Today he's gonna talk about what you can read there. Okay, so Muhammad, thank you. The floor is yours.
Thanks very much for the introduction. Assalamu alaikum. Hi, everyone. This seminar is on task offloading in cloud and Internet of Things environment. So we have two corners of the focus area of this seminar. One is cloud computing, and the other is Internet of Things, or IoT for short. So we'll go over the background of cloud computing and IoT, the tasks, different types of tasks that are generated between these two entities, why they are generated, what are the different types, how they are generated, and we'll go over the technologies that make these two entities, cloud and IoT, come together and talk to each other. We'll go over the reasons why do we offload tasks. We'll go over the technologies that enable this task offloading. And in the end, we'll go over some of the interesting use cases, that's especially the ones that we have been working on here at CMU. So let's start with the background, the preliminaries. We have cloud computing, the one side of this discussion. So by now, I think everyone knows that cloud computing has nothing to do with these clouds. So we'll get to the point directly. We have cloud computing, which is defined as a set of resources such as compute, memory, storage space, data, and applications. The resources are made available through a set of servers that are known as data centers. The data center is available over the internet. So the motivation behind cloud computing was to have the resources ubiquitously accessible to everyone. Another reason was not to have the necessity to purchase the resources. Rather, you can rent the resources and you can pay on pay-as-you-go basis. So you would access the resources from anywhere in the world and you would pay for whatever you have used out of those resources. Some well-known examples, you have Dropbox for storage cloud, you have Amazon for compute, and you have YouTube for service. The other side of this discussion is on Internet of Things, or IoT for short. So generally, when we talk about internet-connected devices, that the thing that comes in our mind is the devices that are able to talk to other devices over the internet directly. For example, smartphone, computer, etc. But the vision of IoT is beyond that. IoT says that you can connect anything to the internet, anything including the dumb objects. For example, you're building a tree, anything, a vehicle, a living being. So that's the vision of IoT. Let's see the interesting history of IoT, how it all evolved. So do you recognize this thing? This is the logo of School of Computer Science, CMU, and it all actually started here. In 1982, CMU CS department. The idea was, instead of walking down to a vending machine and then discovering that there is no Coke available, what they did was they installed some sensors in the vending machine and built an application on top of that. And based on that, you could check the statuses of the cans on your computer. So that was a little bit of laziness with the intelligence. Combine both these things, you get smart applications. So that was the very first thing that was connected to the internet. And that very first thing was a Coke vending machine. So this shows you the passion for Coke as well. And science also backs this fact, that sometimes this laziness comes in handy if it is coupled with intelligence. So on one side you have cloud computing, on the other side you have Internet of Things. Now, cloud has practically unlimited resources to offer. Cloud has the capability to perform extensive tasks. On the other hand, you have IoT that has heterogeneous objects in that, heterogeneous instances. They are devices that can communicate. They are dumb objects that cannot communicate. So all those things would be, they would require some entity to perform tasks on their behalf. So those IoT things would be looking for a cloud to perform tasks for those IoT entities. On the other hand, since cloud is abundant in resources, cloud would be looking for receiving data from different sources so that cloud can build applications based on that data from different sources, different services based on different conditions. That is why both cloud and IoT would talk to each other. So once they talk to each other, they generate tasks in different forms. Mainly those tasks are of three types: data storage, computation, or application, which is contained in a virtualized form known as container. We'll learn more about container and this slides as we move along. So the tasks are sent from one device to another device, which is known as task offloading, or also known as service delegation. So once cloud and IoT talk to each other, since IoT has dispersed objects in it, this means that on several locations, the cloud won't be able to access those entities, those things. So cloud would need a middleware entity, something in between the cloud and the IoT, so that the middleware entity can make both these entities, cloud and IoT, talk to each other, discover each other, or perform service level agreement, matchmaking, and stuff like that. So that middleware is necessary to make these two distant entities talk to each other. And we'll go over some of the middleware technologies up next. So the first one is cloudlet. As the name suggests, that cloudlet is a small-scale cloud, the same resources that a cloud has, but at a smaller scale. And the other thing is that this cloudlet is localized, so it's available for the mobile devices. The idea was to have low latency by putting the resources close to the underlying users, underlying mobile users. So this is entirely for mobile users, and what you would get is you would get low latency because the resources are close to you instead of accessing the over the internet cloud, the traditional cloud. So this was the concept of cloudlet, and it was introduced by CMU. So Cisco in 2012 extended this concept. Cisco argued that instead of having just one entity that provides you services, that entity is small scale, so we cannot generate intensive applications. We cannot have machine learning based applications. We need a resourceful entity that is reliable. Whenever we need to offload something to that entity is available for us and can perform extensive tasks. So the argument of Cisco was to have a 3-layer architecture of middleware in which you have the underlying nodes using this, the application or service, and you have the distant cloud that has all the resources. So a middleware entity, Fog, would perform the necessary localized tasks for you, so you can eliminate the delay factor or minimize the delay, and also perform personalized services. And in case you need to offload something to the distant cloud, then you can perform that thing as well, which was not possible in the case of cloudlet. So you have 3-layer architecture. HC in 2014 amalgamated both these concepts, fog computing and cloudlet. So what they did was they said that, okay, fog is good, we endorse this 3-layer architecture. But the problem is that fog is generic. Fog is not for mobile devices. So what we should do is we adopt the same 3-layer architecture, but we incorporate the cloudlet attribute of providing resources close to the mobile devices within the radio access range. So their concept was to have the cloudlet plus fog computing stuff. This was another type of middleware. Then we have edge computing. Edge computing refers to user-owned devices, your computer, your smartphone, your smart glasses, stuff like that. So some researchers confuse edge computing with fog computing. They would both use them interchangeably. But according to Open Fog Consortium's reference architecture, which is backed by organizations such as Cisco, Intel, Dell, ARM, Princeton University, and some other well-known universities, their definition of edge computing is solely your end-user edge devices, user-owned devices. In case of fog, it would be owned by some other entity, and it would be relatively less localized as compared to edge computing. When you combine the resources of your edge devices, they become femtocloud. Another technology for middleware tasks is delay-tolerant network. Delay-tolerant network, or DTN for short, comes in handy in those situations where you don't have an end-to-end connectivity. So to reach out a distant, not connected destination, what you would do is you would find an entity that connects to the source and is anticipated to reach out to the destination at one point, at any point. So through this concept, you would offload tasks to this intermediary entity, which takes your task to the destination. So this type of architecture comes in handy where you don't have connectivity, or reliable connectivity, for example, in the rural areas. In the form of a layer, this is how middlewares would be. So on zero hop, you'll have these devices. MIST is a Cisco terminology. And on one hop, you have the fog devices. So you would choose the middleware based on the type of your service, plus this can be based on scalability. You may have more than one middlewares as well. Then you can reach out to the distant cloud over the core internet. Let's see what are the reasons for offloading. So I think you might have guessed some of them, if not all. Excessive computation is one major reason. If I cannot perform a certain task on my own device, I would obviously offload that task to a device that is comparatively resource rich. Another reason would be latency. So as we've learned going through the middleware entities, that localized fog or localized cloudlet would be close in proximity to me. So I would, or the service provider would, offload the tasks to their entity so that the users can get the service within a acceptable latency. Another reason would be load balancing. So in a data center, if I have multiple requests coming in, based on my own condition, based on the number of requests, based on the type of request, the size of request, I would distribute the tasks to my own data centers or my different middlewares. So I can have multiple middlewares as well, and I can balance the load. Another reason would be permanent or long-term storage. If I need to store something on my phone, for instance, then it's not possible forever. So it is possible for a few years probably, but not forever. So what I would do is I would offload that file or that data to an entity that can store the data forever or for a long time, which might be a cloud. Data management is another reason. I'll distribute my files. I'll put my files in different ways on different devices based on my usage, based on the type of that device. Also, privacy and security would be another reason. So for example, in a hospital is getting data from different sensors. The hospital would prefer to take that data and put it in a private cloud rather than putting in the random servers within that hospital. So that would be more privacy aware. Or if you need additional security, then you would put that data to a traditional cloud. Another reason would be accessibility. So if I need to access some files that are on my home computer, I would put those files on a traditional cloud which is accessible always over the internet. Another reason would be maintenance or affordability. For example, we have our own data center here at CMU, and that data center is used by some other universities within Education City. So they don't have to maintain their own data center. They are outsourcing stuff to us. They are offloading tasks to us, and then we are providing the services to them. So these are the main reasons. A 2-second break, I guess. What are the technologies that enable task offloading? So I think convenience is the simplest answer. Anything that makes it possible plus makes it convenient are the technologies that we require for task offloading. The first and foremost would be wireless technology. So if I can offload my tasks on the go through wireless technology, that's the first thing I would need when it comes to task offloading. When I'm thinking about having a rich application that can provide me resources, that can provide me intensive tasks, resource-rich tasks, based on my priorities. If I need a task locally, I'll use a middleware entity. If I need a task which has deep learning type of stuff, I would offload that task to the traditional cloud. So the wireless technology provides me that thing through wireless broadband, for example, or direct connection one-on-one, which is Wi-Fi direct or Bluetooth, or the traditional data network 4G LTE, which provides me 100 Mbps, or with 5G technology, I can have more than 100 times of today's 4G speed. Another enabling technology would be smart and autonomous applications, which means those applications that are context aware and that are based on machine learning. Applications that are intelligent enough to decide what to offload, when to offload, and where to offload. In our NPRP project, we have built one application of the same kind, that is smart and autonomous application. Another technology would be virtualization and containment. So virtualization, in short, is softwareization of a hardware, softwareization of a physical entity. Virtualization in general has two types. One is virtual machine and the other is containerization. In case of virtual machine, what I would do is I'll virtualize the entire physical machine, including the operating system, including the libraries and everything. So it's a rich virtual machine with everything that I need, everything that a physical machine contains. I have the same stuff in the virtual machine. But of course, it's large in size. So if the large size matters to me, what I would do is I would contain it in a smaller form. The smaller form is, instead of containing the entire operating system, what you would do is you would only associate the relevant libraries and bins of your application. So if I have an application running on my computer, instead of taking the entire operating system with that, which is the virtual machine, what I'll do is I'll just take the associated libraries. So it's less secure, but it's lighter in size. So that also enables task offloading. If you need security and you have enough bandwidth, or you can wait for transmission of the task, then you can use virtual machine. This is one enabling technology. Or if you have an issue with the size, then you can use this technology, container, to offload your tasks. Similarly, parallelism, multi-core technology enables this thing that you can divide your task into different subtasks and then perform the execution of the task so that you have the results much faster. Let's go over the use cases now. Okay, so do you know how much time people generally spend on their phones on average all around the world? This much. And this is up to more than 4 hours a day, which means 17% of your day on average is spent on mobile phone. So this is how much we are present online, and this is how much data we are generating in only 1 second over the internet. So we have these many applications that are reason to generate the data. This many videos, text messages, emails, and stuff like that. So with that amount of mobile phone usage and this much of data generated and these many applications that we have, our online presence results in eating up our storage space on our devices. That's a problem. So what's the solution? This is the solution. Get a device with higher storage capacity, but it comes at a cost. That's the problem. What's the solution then? Delete your files manually? Is this feasible? Maybe not. Why? Because this is a time-taking process. Also, you may not be willing to delete some of your files that are probably not that popular or you're not using them that much, but they're still important to you. You still want to keep them. You're not using those files every other day, but you still want to keep them. So in that situation, what is the other solution then? The other solution is to use a cloud service. But cloud service comes with a cost. If cost is not a problem to you, maybe privacy is a problem to you. Then what's the solution? The solution is when we were going over the middleware technologies, we learned that we have femtocloud as a middleware as well. Why not aggregate the resources of your femtocloud in this form and then offload your tasks or your data to other devices? Research is back that on average, every person has more than 3 internet-connected devices, at least 3 internet-connected devices. So if you have at least 3 internet-connected devices on average all over the world, why not make use of those devices? For example, right now we have this many number of people here, assuming that every person has 1 smartphone, assuming that every smartphone has on average 1 gigahertz of processing capability and some storage space as well. We can make use of this underutilized resource pool. We can, in the same way, we can make use of the entire resource pool of CMU as well. When we are in the office, during the office time, we can make use of these resources. So the benefit would be, number 1, we're cutting the cost. Number 2, it's more privacy aware. Instead of sending your data to a cloud, which you might not be willing in all the situations, you can do this thing. So this is the concept of shared economy, same as some of the well-known services have adopted this concept. For example, Uber is the largest taxi company without a single taxi owned by them, except the upcoming autonomous vehicles they have. Similarly, you have Facebook, the largest media owner, without a single media content created by them. You have YouTube without a single content created by them, so they're sharing the resources. You are creating things, you are using things. So both the creator and the user are the users of these service providers. We do the same thing here at CMU. We provide you the femtocloud resources. The solution is that you have your files. In the beginning, you don't know. Actually, we don't know which files are popular and which files are not popular. So we have an algorithm that determines, based on your usage pattern, which of your files are used most often, which files are not used often. So based on that, we determine the popular and unpopular files out of your native device files. And what we do next is, so how do we do that? We do that based on these 3 factors. How many times you're accessing your file? What is the access spread? For example, this one. What is the access recency? For example, this one. Now in this example, this is the burst of accesses, and then the file was never accessed again. This is a decent and consistent access pattern. The file was created over here, but then recently accessed in a burst. So this is probably based on some event or something. There is a spread, long distance in terms of duration in the access of file. So based on these factors, we determine which files are your popular files and which files are not. And then we can offload them. So these factors are actually gauged through these 4 metrics. We have these 4 metrics. How many times your files are accessed? What is the distance between every consecutive access, distance in terms of time, and the total lifetime of that file? The file lasted for example, 6 months, file lasted for 1 year, file lasted for 1 month, etc. And to determine that this burst access, to cancel out that element, we use cluster ratio. So you have 2 consecutive access as 1 cluster. Based on that, we'll determine that if the file was used in a specific pattern or it was just a burst access. So this is the further detail of this thing, and we can, I think, go over this part. So my top 1% files, that are my most popular files, 90% of the times, or actually if I look at here, my top 1% files are accessed with an intercession length of 1,000 minutes. So this shows that my file would be accessed, this is somewhere around, I think, 16 hours or so. So this shows that I'm accessing my most popular files on average twice a day. Other than that, my access would be something like this. So my 99% files are accessed like this. This is, I guess, 100,000, which would be, I think, 70 days or so, 69 days. So based on that, we determine which files are popular and which are not. In the same way, we have another algorithm which determines which devices are popular and which are not. Popular devices means the devices that have higher capacity and they are accessible as well, because I'm offloading my data to another device, so I need to access it back again. So I need to make sure that if I have a file that I need to access on average, for example, 3 days, can I access it back? What is the percentage? Based on that, the algorithm determines this thing and then offloads the files to that entity. So we evaluate this system, our developed system, based on 3 environments: metropolitan, urban, and rural. Metropolitan is defined by stable Wi-Fi and stable data network. So you have the luxury of connectivity, always on connectivity. You have rich people and you have sophisticated devices. And in the urban environment, you have stable Wi-Fi, but unstable data network. In the rural environment, you have unstable Wi-Fi. Everything is unstable actually. So you rely mostly on Bluetooth and Wi-Fi direct. This is one-on-one connection. So we take care of the underprivileged devices as well here at CMU. So the results show that in the metropolitan environment, if I offload 90% of my files, so I have my files, now I know that which of my files are popular and which are not popular, based on that, and plus based on which devices are more accessible to me, which devices are popular and not popular. Based on that, I'll offload my files. So if I offload 90% of my files, then if you can see here, this blue one, this bottom one, 90% of my accesses here, 90% of my accesses are within 10,000 milliseconds, which is equal to 10 seconds. So isn't it acceptable? Because you're saving your files. You're still keeping your files. Plus, they're privacy aware. You don't need to send them to the cloud. In urban environment where the connectivity is not as good as metropolitan environment, the accesses within 10-second delay is 75%. In the rural environment, the accesses are almost half within 10-second delay. So if you can tolerate some more delay, this performance would be accordingly enhanced. So this is the solution related to data offloading. Sure.
So how do you model this when you have the idea that, like, okay, so offloaded some of my files onto my tablet and I left it at home that day. It's not less than 10 seconds, it's like 24 hours. Like, how do you model this?
No, the device should be connected. So if this is a metropolitan environment, for example, if you're living in the metropolitan environment, we assume that your device is accessible over the internet. You have stable Wi-Fi.
What about like your rural environment?
World environment?
The rural environment.
Rural environment, yeah. So in case of rural environment, either you have Wi-Fi connectivity, if at one point you don't have a Wi-Fi connectivity, because we're not saying that there is no Wi-Fi at all. It's just unstable. So if you do have Wi-Fi, then you are accessible. If you don't have Wi-Fi, then yes, you have to rely on this thing. So it depends on that.
Right, so you still have scenarios where the file just simply is not available because the device isn't online and isn't with you.
Yeah, so actually we map this thing based on different accesses. For example, if I'm accessing my file from the device that is sitting at home and the device is not connected to the Wi-Fi, then I cannot access that file. Okay? So I'll go back home whenever, for example, in the evening, and then I'll retrieve my file. It takes me, for example, 8 hours.
Sure.
In another scenario, I have that device connected to the internet because there might be Wi-Fi available as well. So in that scenario, I'll get the access within 1 second. Based on these several accesses, the average is that on 45% of the times, you get this within 10 seconds. This is how the average is.
So, do you offload the whole file or chunks of the file?
We offload the entire file.
And then what if so now you need to know the storage dynamic. You need to know always the storage is available.
Yeah, it's dynamically changing.
And
Yeah.
then if you have a set of devices and you have a whole file that cannot fit on any one single device, will you chunk? And
Yep.
you
In
do all
that
these
case,
kinds of things?
yeah. In that case, we'll chunk the file and then divide into different devices. Because they're my own devices, they're my user-owned, they're my household devices, or they're my family devices, so I can trust those devices.
And do you replicate in case if one device is offline and I want as a user to access my file, if you replicate, I can actually still access probably from
Yep.
another.
In case of replication, you're consuming additional storage space. So if you do have that luxury, you can do that. You have enough space, then yes, you can replicate at any point. But if you don't have, so right now we are working on this thing actually.
So offloading means migration, not,
Yep.
so you don't keep a copy at my site as a user.
So far, up to here, no, we don't. But right now, we're working on this thing. This is the next part of our work, that we have to replicate in some scenarios. So replication, so we are currently working on compression techniques, that what are the different compression techniques that enable the replication more efficiently. So yes, you can replicate, but then obviously there is a compromise.
Consistency.
Yep. So, but actually, this is not for commercial users. This is an application that anyone can use, but this is based on your own devices, your personal devices. So you have to analyze that how many devices do I have and what is the capacity of my devices. So once you run this application, for example, then based on your devices, your capacity, your resource pool, it would decide that how much luxury you can have or how much benefit you can get out of it. In otherwise case, you have to offload to another entity. So it depends on your devices as well. As we have seen that the average says that every person has at least 3 devices. So some people won't have 3 devices. They'll have 1 device, some others would have 10 devices. Based on that, you'll have your resource pool. So another use case is computation offloading. So let's see this example of computation offloading. So let's talk about smart waste management. So generally, the way waste is managed is that we have one waste bin, and we dump everything in that waste bin, including organic, inorganic, paper, aluminum, all that stuff. So for example, in the US and Canada, we have one fixed day of the week where the waste managers would come and they would pick the waste. So it is possible that the waste bin is already full, probably it was full 2 days back, or the waste bin is still not full, it's half full. So in that case, when the waste manager arrives and they checks the waste bins, this is resource either underutilization or you're letting the bacteria take birth and bad for health. So this is not a good solution. What is the solution in this scenario? The solution might be that you have segregated waste bins, each waste bin for different kind of waste. For example, you have one for paper, one for organic, one for plastic, etc. And each waste bin is equipped with a sensor that tells the level of the waste. Okay? And then you have a metropolitan fog or any other middleware. Let's suppose in a residential compound you have different waste bins. In that compound you have one fog that collects the data from all those sensors, all those waste bins within that compound. Or in an apartment building, for example, in West Bay, you have a cluster of buildings, and then you have one or more fogs that are collecting the data from all those waste bins. Based on that, the fog will create a optimized route and inform the waste managers to, instead of traversing the entire city, just move around this path and collect the waste because it has to be collected. The waste bins are full. So in addition to that, the fog can offload this task, the rest of the data, to the cloud, and cloud can perform deep learning based tasks on this and create further services. For example, services related to healthcare, services related to recyclers, so that they can analyze that in this particular month or in this particular quarter, we are going to get this much of paper waste, we are going to get this much of organic waste, etc. So we can manage our resources accordingly. How much of the stuff we need to import based on this, they can decide beforehand. How much of the stuff we can export, they can decide based on this thing. And also, the government can analyze that if, for example, we have a particular kind of waste in a particular locality, what might be the reason? For example, if in a particular locality, people are mostly the wastes are related to packaged food. So what's the reason? Why are people having more packaged food in that particular region? Is it because they're living a luxurious life, or is it because they don't get enough time to cook the food for themselves? So probably they don't have a good work-life balance. Should we do something to make it better for them so that they can contribute well to the society? So all these things can be done through this kind of an idea. And a food for thought is that 33.33% of the food produced in the world that goes to waste. So you can analyze this stuff as well based on this kind of an idea. Further details on food wastage is here. Almost half of the fruits and vegetables all around the world, they go in waste. And the major contributors are Europe and North America. In the same way, you have other commodities. So in the same way, we can have a different scenario for this use case of computation offloading. Currently, when there is an emergency situation, what we do is we have to call the emergency dealing department, for example, 911 or whatever country you're in. So what you do is you make a call, you give them your location, you explain them your entire emergency situation. Then they digest that thing, and then they decide which emergency dealing department should be contacted, fire, police, ambulance, whatever. And then they figure out your location as well. At some point, you might not be able to tell your location because you are in the middle of nowhere, or you're in emergency situation, so you're panicked, so you don't know the location. Another obstacle would be if you're in a country where language is a barrier. So how would you explain everything on the phone? An easier solution is to have a mobile application that has all these options. So you just click the relevant option, and the mobile phone sends your location through the GPS sensor. The nearby fog, for example, a metropolitan fog, receives that information from you and then translates the location and then finds out the optimized route for the relevant emergency dealing department. So this might be important in countries like here, where you have road change every other day, and you don't know which route to follow because the navigation apps take their time to learn the new routes. So with this, since you have a localized fog, you have your city fog. The city fog can be manually updated as well based on the location. So based on each update, you can perform this stuff. Then the fog can offload the rest of the data, the mined data, to the cloud, and then cloud can create further services for that based on that data. For example, these services can be used by insurers. These services can be used by health department, road safety infrastructure ministry, etc. Why a certain type of accident is happening at a particular location? What's the reason? Is it because of the road condition, or is it because of the lighting condition? It is because of some other reason. So you can achieve all these things based on this type of task offloading. And in the same way, you can have this scenario as well for intelligent transportation system. So you can have sensor-equipped vehicles, private vehicles, cargo vehicles, passenger vehicles. They have sensors related to the driver to monitor driver's health. They have sensors related to the passengers to monitor passengers' health, driver's compartment, cargo health, and all that stuff. Based on these sensors, you can not just assist the driver and avoid any incident, but also you can guide based on the traffic conditions, based on the weather conditions. Plus, the data can be in real time sent to the stakeholders, for example, the recruiters who are interested in the driving behavior of a particular driver, or the traffic police. And you can manage your traffic signals smartly as well. So this comes in handy in the situations where you have different traffic loads at different times. Plus, if an emergency vehicle is approaching, you can clear up the roads well before time so that you don't have the hassle of congestion or the vehicle doesn't need to honk everybody. In the same way, you have scenarios in healthcare. For example, a hospital is receiving data from different sensors. The hospital builds applications based on those sensors. And this includes the technology of virtualization through virtual sensors. So the hospital doesn't need to purchase different sensors for different conditions, but they can use the virtualization technology and make use of same physical sensors for different applications, customized applications. Then you can secure the data and send to the cloud, and the cloud can perform further services, for example, early diagnosis or ambient assisted living and things like that. You can have an entire ecosystem of healthcare that includes your pharmacies, includes your patients, includes your hospitals. So if you're purchasing a medicine, the entire system, since it's a connected system, would be able to tell you if this medicine goes well with your previous medicines that you're already taking for another disease, for example. Let's see some representative results based on this computation offloading. We already saw some results based on data offloading, so this is related to computation offloading. The purple bars represent the task length in billions of instructions. As you can see here, the tasks grow. The red line represents the delay when you send these tasks to a cloud versus the blue line represents the delay when you send these tasks to a fog. As you can see here, fog's performance is much better than cloud's performance. But is it always the case? No, it's not. There is one point where cloud and fog intersect each other, and actually cloud overtakes fog in terms of delay performance. So this shows that it depends on the task length, it depends on the capacity of your middleware entity, and it depends on your priorities, whether it's a privacy-sensitive application, whether it's a localized application. You really need a fog for that. So there would be a point where it would be much better to distribute offloading between two entities. For example, offload these tasks to a fog, the rest of the tasks to a cloud. Is it okay for you? If not, you don't want to compromise on this thing, then you need to enhance the capabilities of your fog. Please have a look at these three first bars, the purple ones. They represent the task length again. So if you have processing capability in your fog of 0.125 gigahertz and the task length is 10,000 billions of instruction, the delay incurred is 80,000 milliseconds, and the processing cost is $0.002375 per hour. If you increase the capacity of your fog from 0.125 gigahertz to 1.25 gigahertz, then the delay comes down to 20,000 milliseconds from 80,000 milliseconds. But the cost from 0.00, this is increased to $0.0095 per hour. As you can see here, these are the tasks. This was the initial delay. After enhancing the capabilities of your fog, your delay comes down to here, which is pretty good. And in this case, you had the cost in the beginning this, but now after enhancing the capability, your cost is increased this much. Similarly, your processing power was here and increased to here. So it's a compromise. It depends on your priorities.
What are the factors into delay? I'm just noticing, like, you increase your processing by a factor of 10, but the cost only goes, or the time only goes down by a factor of 4.
Yep.
It's like, what else contributes to delay other than the amount of time to compute the task?
So the cost is based on the cost of processing only. That's it, nothing else.
Then why does that factor of 10 increase in processor speed only result in a factor of 4 decrease in time?
It depends on how much you offer for every resource. So we are using Amazon EC2 for this cost analysis. We use the cost of Amazon EC2 to analyze how much it would be if we increase the capabilities from here to here.
That's not what I'm asking.
Yeah.
So you have 0.125 gigahertz.
Yeah.
You increase it to 1.25 gigahertz.
Yeah.
That's 10 times faster.
Okay.
But the time goes from 80,000 milliseconds to 20,000 milliseconds, which is only a factor of 4 decrease.
Okay.
So why does your processing multiply by 10, but your speed, but your delay only decreases by a factor of 4?
So it depends on the task as well. So in this case, the size of task, and then the same task, if it is run on this capability, the delay factor would be accordingly changed. So you got the answer or still?
No.
Okay.
So you already, I mean, you defined length of task by the number of instructions.
Yep,
So
billions
the
of instructions.
processor's 10 times faster. It can run
Yeah.
it can run 10 times as many instructions
Yeah.
per second. So I still don't understand why your time only goes down by 4.
So it's not just sending from one node to another node. This is the end-to-end delay. I have a fog and I'm sending the data from fog to cloud, or I have a IoT node, I'm sending the data from IoT node to a fog
So this
versus
also
to,
includes communication.
yeah, communication includes.
Okay.
Yeah.
So I
And even if only computer includes processing power, it's not linear, it's known in systems. You cannot have linear speed up
Right,
if you increase that.
it's not linear for normal workloads,
Yeah,
but it
because
gets
you have the
modeled,
cache,
it would
you
be.
have the memory, you have the accessibility pattern of the application. There are many, many factors that play in. It's known by Amdahl's law, you don't get linear speed up.
Right, but this is modeling it in a simple way with just number of instructions executed, which
Yeah,
would
it
be-
includes the number of entities between these two entities. So it's an end-to-end delay.
Sure.
So the third use case is application or container offloading. So when you need to offload an entire application, you need to contain that application in a virtualized form. So as we discussed in the beginning, that we have two forms of virtualization. One is virtual machine and the other is containerization. So if I contain my application, entire running application, then I would be able to offload my entire application from one node to another node. Let's see this example that, for example, you have a cop with visual sensors installed on the cop through, for example, smart glasses with camera or a body camera. And the cop is monitoring a certain event or a location, and the cop moves from one location to another location, or the cop hands over the duty to another cop. In that case, the cop's data coming from the sensors to his phone or her phone, and then to the fog, this should be migrated from this location to another location. So this would be made possible through containerization, which is another form of task offloading. One form was data, the other form was computation, the third form is container. And since this is related to multimedia, this is related to video or image, we analyze 3 different types of videos to see if this makes sense or not. We have these 3 types, and then we have different bandwidths. Depends on whatever bandwidth you can access in your situation. Plus, we don't know the distance of these 2 locations from one location to another, so we use RTTs for that. Based on that, we analyze and we get these initial results. We're still working on these things. So you have these 3 types of videos, 360, 480, 720, 3 sizes of video, plus the distance between the 2 locations through 50 millisecond RTT, 150, 250. You have this purple one for sending delay, you have the blue one for receiving delay, and you have this encoding, which is the processing delay as well. So this is in seconds. The delay grows as the video size grows, or the delay grows as the distance grows. So this is the maximum one. And I think that's it. So the bottom line is to avail the resources that you have, make the best use of those resources, and compromise wherever you have to compromise. You have to make the decision of where to compromise. That's it. If you have any further questions, you are free to ask.
Can you shed some light on the major challenges of pursuing these kinds of applications? You spoke a little bit about replication, synchronization, especially when it comes to the traffic light thing. Different things might have different times. You need probably to synchronize clocks. Can you shed some light on these kinds of challenges that you encounter?
Challenges related to these scenarios, these applications? It
Yeah,
depends
from a
on
systems
every...
perspective.
Yeah, it depends on every application. So every application has different challenges. One challenge would be the government itself. For example, we talked about different middleware entities, okay? Fog is a middleware entity that is owned by a third party. For example, your government would be owning that, or a vendor would be owning that. So the owner of a fog would be either Cisco, for example, or the government itself. So if the government allows that type of service, then you can avail that. Otherwise, you don't have a choice. Then you have to use edge computing. But edge computing is more localized than fog computing. So in that case, you won't be able to do these type of things. So legal issues would be one reason. Privacy issues would be one reason. Privacy might not be a problem in some countries, but would be a problem in other countries. So it depends on that thing as well. And also integrating different sensors, different heterogeneous entities, objects, devices. In IoT, we have all sorts of devices, all sorts of sensors. Even the devices that are communicating devices, they are built by different vendors. You don't know which protocol they're using. So you need an entity that can translate the protocols or that can integrate those entities as well. So that is another issue. Yeah.
And all these applications are simulated. You haven't had any actual applications all simulated on?
Yeah, as I said, that these applications depend on legal issues and government as well, so they are, yes, simulated. None of them are practically implemented except the data offloading stuff.
Any other question, guys? No questions? So let's thank our speaker.
Thank you so much. Thanks very much for being here.